So I don't remember if after we got back from the break I was telling you about the book that I read. I think I kind of was with you guys. I told you a little bit. But people argue about this all the time. Like, are we spending way too much time in the weeds of solving equations that ultimately you can plug them into online applications that will solve just about any kind of math problem for you easily, you know. Um, Other people say, well, we shouldn't be focused on that. We should be focused on data, because these days we collect so much data, and data without some kind of pattern to it that you recognize or do something with is just a bunch of, miscellaneous information. This is kind of where the two sides meet, where we're actually going to look at data and then use the math equations to make sense out of the data. And that is kind of, anybody that thinks that we do too much math, ultimately, this is very practical stuff. Whether or not you go on to be a mathematician or a social worker or whatever you do, you probably find yourself having, sheets of information that you're trying to make sense of. Maybe you did a survey of the people you serve, and whatever the thing is you were asking them questions about, now you want to look at that information and see whether there's some kind of relationship between different variables, something like that, because maybe that would help you to make decisions about what you have to do. So this is pretty important. We don't do much with it here. We do linear, but there's other things that we'll see in the calculator that you can do with it. We can do more complicated functions, but linear is by far the most important anyways, and that one we're responsible for doing now. Okay, so that's what this lesson is. And since you got to do it in a calculator, what we do in class, what we do for homework, we'll just do in class because you have it right in front of you. Now, I don't know if anybody, remember, you can get, if you have an Android phone, there's the Wabbit EMU, which is the same emulator that I'm using right here. I mean, that's free. You can go out there and get it and download it to your phone and have that. And it's like you have that in your hand. It does everything that does right there. So even without the graphing calculator, you can have the capability of the graphing calculator at home. And that's what we're going to be using today. But you have to follow along. You got to be actually trying to do these things, because on the test you will have to do these. I'm not going to answer these questions during the test. You have to have learned how to do this. So we know that 2 points uniquely determine a line, right? Meaning, what does it mean when I say uniquely? Meaning, if you have 2 points, there is only one line, one straight line that would go through those 2 points. But what if you have 3 points? I mean, could you make one straight line that goes through these 3 points? No, you can't. You could maybe draw a line through 2 of them, and it would miss the 3rd point, right, in some way. Or you could draw a line maybe through the middle, something you felt like was more an average, It was missing the points, but it was the closest you could come to all 3 points. So that's where we're at now. And when you collect data, even if there's a linear relationship in the data, for example, if I looked at your paychecks and you were getting an hourly wage, I wanted to know how much did you get paid based on your number of hours that you worked. It ought to be a straight line, but maybe you have taxes taken out or whatever is the difference. Even when there is a perfect linear relationship, when you collect the data, maybe it doesn't quite look so clean. Maybe it's a little messy, that one point isn't quite on the line. That's what we have to deal with now. And, most of the time, we're dealing with a lot more than 3 points. Now, if you go back to the SOL and what it asks us to do, which I actually just noticed this when I was doing this. Where is it? It says, given a set of no more than 20 data points. I say 20 data points, that's a lot. I don't know if I wanted to have that many data points, but no more than 20. So there's not going to be one unique line that approximates these points. If I asked all of you to draw a line through there, you'd all have something that was just a little bit different, right? Okay. Let's get the calculator. Take that. Okay, I'll get it later. So here's a lot of these, because it's data and the data was actually collected to be about something, they're word problem kind of things. The table shows, misspell, the number of active red-cockaded woodpecker clusters in a part of the DeSoto National Forest in Mississippi. Write an equation that models the number of active clusters as a function of the number of years since 1990, right? And write the equation of a line through the plotted points. Actually, I kind of repeat myself there. Okay, first of all, when it says that write the equation of a line, that the function of the number of years since 1990, what that means is you don't want to use 1992, 1994, etc. on the graph. You're going to instead put in how many years is that since 1990. So in 1992, how many years is that? It's 2. So I'm going to make a column here, and many of these problems, they have years in them. So you have to say, okay, but my x value, I'm going to make that into 2, and then 4, and 6, and 8, and 10, right? That's why I have that scale and not 1992 and 1994 and things like that. Okay, these are the y values right here, the active clusters. Okay, so then we need to graph these points, right? 222. 222 is about right there. And 427 is about right there. And 634, 842, and 1051. Does it look like it's linear? Do they look like they would all fall pretty close to the same straight line? Yeah, it does kind of look like that. Let me draw a line that goes through those points. Let me change the color. Something like that. So does it hit every point exactly? No, it's kind of, I have it going through 2 points on that line. And it's missing 1 point that looks like it's below the line and 2 points that look like they're above the line, but it looks like it's kind of going through the middle. So if we want to come up with the equation of that line, we know how to take 2 points and turn them into a line. So you would just look at the graph and come up with 2 points. Like, how about if I pick these 2 points? That one and that one. I mean, they're in our table over here. 427 and 842. I mean, my line went through those 2 points. So if I use those 2 points to make the equation of a line, that'll be what I get. Right? So that's the first thing. When you graph the data, you look at it. If it looks like a straight line is a good approximation of it, you can take 2 points and do what we've already done in this unit, right? Find the slope, use slope-intercept or point slope to come up the equation of a line. So using those 2 points, I think I have this on the next slide. 427 and 842, let's make our line. First step, if you have 2 points, first step to make a line, find the slope. This one, the slope is 42 minus 27 divided by 8 minus 4, which is 15 over 4. Next step. Say again. You could do the y equals mx plus b, like we were doing. Y equals mx plus b. Right? The 15 over 4, that's the m. So y equals 15 over 4 x plus b. And now we need to find the b. So what will I do? Plug in a point, right? Does it matter which point we plug in? It doesn't. I'm going to use this one because it's less. The numbers are smaller. So this is 27 equals 15 divided by 4 times 4. Well, that's convenient. Plus b. The 4's cancel. Cancel, cancel. So we can do 27 equals 15 plus b. So what does b equal? B equals 12. So here's our equation of that line that we drew on the last page. It is y equals 15/4 x plus 12. Right, and that was, we did that, oops, that was too far. Using this data right here, 1992 to 2000. Now, who knows, maybe they did this in 2000, but we're not in 2000 anymore, right? We're in 2016. What if I wanted to know what this would have predicted for the number of active clusters in 2016? How could I use my line to figure that out? I would have to plug in for X, right? What would I plug in? Would I plug in 2016? Well, the years since 1990. So 2016 minus 1990, it's actually 26, not 16, right? 10 years from 1990 to 2000, another 16 years. So if we wanted to know 2000, or 2016, we would plug in 26 there, and we would get a prediction. Do you think that would be a good prediction? Probably not. And when you try to make predictions that are like far away from the data that you collected, then you're less likely to get a great answer. Just like a weather forecast, it's good for today, not quite as good tomorrow. You go a week out and they don't even tell you what they think anymore because they know it's not very accurate. So try to plot those points first. Make a graph the best you can, and then draw a line through the points. The best straight line you can. So yeah, if you don't think that those look quite linear, I agree. They look like there's a little bit of a curve. Like maybe it's kind of like that kind of a shape, right? But still, at this point, we're going to try to find the best line that we can that goes through the middle of those points. In fact, you'll see when we get to doing this with the calculator, we can use other functions that are not straight lines to approximate something like that. But if not, I would think I'm maybe going to draw this line to go, maybe I'm going to hit this point, and maybe I'm going to hit that point. So draw yourself a line, just hand draw the best you could. Use a straight edge or anything you've got to try to make that a straight line. And then circle 2 points that you think are on that line. I mean, if it's up to me, I'm going to draw the line so that it actually hits 2 of those points. And I think I did. So I'm missing some points on one side and some points on the other. It's kind of going through the middle, but I think I've got these 2 points are definitely on the line. What's that? Is it? Sorry. So which 2 points are those? It looks like that one and that one. So make the best the equation of a line that goes through those 2 points, just like we've done in this lesson. Find the slope. What do you get for a slope? 7/4. So m looks like it is 12 minus 5 over 6 minus 2. M equals 7/4. So now I'm going to plug that in. Y equals 7/4 x plus b. Okay, then use one of your points. Does it matter? 2 and 6. Probably 2, 5. Let me do that. 5 equals 7/4 times 2 plus b. So 5 equals 7/2. The 2 cancels, right? I can cancel that 2 with that, and it leaves a 2 behind. So that's 7/2 plus b. So what is 5 minus 7/2? Say again? 1.5. Remember. So if you got to solve this by saying b equals, you're going to subtract 7/2. I mean, again, you should know how to do that in your calculator. If you, I mean, I would find common denominator. 5 equals 10/2. So 10/2 minus 7/2 is 3/2. But if you don't remember that, then just put it in the calculator. What is 5 minus 7/2? And then do math, enter to make it a fraction. So that would be b equals 3/2. So here's the equation of a line. Y equals 7/4 x plus 3/2. Now, if I told you which points to pick, if you all picked whatever points you wanted to pick, then we'd have slightly different lines. But it'd be pretty close. And the truth is, you don't have to pick points that are in the data. You know, you might pick another point. Like I could pick. I would probably look for a place where the line crosses the intersection of grid lines, so at least I'm getting whole numbers, right? This looks like 7/14. Okay, I could use that and maybe pick another one that's close. So you don't have to take out of the data. You could pick just any point that looks like your line is crossing. But if you can make it so it goes through one of these points, that's just as easy because you've already got them. You don't have to estimate anything. So when you graph a bunch of points like that, that's called a scatter plot. And you need to know that word, scatter plot. And sometimes in the book they're using it, they're making it 2 words, scatter space plot. But I'm just putting it together, scatter plot. When you look at the data, you look at the graph of the points. If it looks like a straight line would be a good approximation of those points, then you would say that the data is correlated. There is a correlation between the x's and the y's. Right? If I made a graph, if I collected data that was your grade points as a function of the number of hours that you study, my bet is that the more you study, the higher the grade point. And if you graphed it, it would look like they're correlated, right? There's some relationship between the two. So correlation is a really, really important concept. I mean, ultimately, like I say, this is the age of big data because we're collecting it. You know, every one of you's got a phone in your pocket. Every time you move, you know, somebody's collecting data because, you know, your location is in there. Everything's in there. So this is the age of big data. And, you know, ultimately, what do people try to do with that data? They try to graph it just like that, and they try to see whether there's a correlation is there something going on between those two? Now, it's not always the case that there is. You could make here's an example. This comes out of a book that I read a while ago, but you could make many different examples of this. This book is written by this guy here who gets famous making predictions of the presidential elections, especially the last two. But this is more of a book about, just trying to learn things from data. In any case, he said, if you did if you tried to graph the number of ice cream cones eaten with the number of forest fires, you would see that there's a positive correlation. Now, does that mean that the number of ice cream cones that you eat causes forest fires? No. But that's the kind of thing, a correlation doesn't mean that the one thing causes the other. It just means it looks like there's some relationship there. Now, people are going to look harder into the data to see, can they explain it? What's going on? I mean, how would you think you would explain why the number of ice cream cones and the number of forest fires seem to be correlated? Yeah, because there's some other variable, maybe the temperature, which is causing both to increase. But people actually, this is one of the things that, it's not only so important, but it's misused all the time, where people try to say that there was a correlation between two things. And just because, it looks like there's a correlation, then they try to infer what you would call cause and effect. And you can't do that. That's like the number one rule of the statistics is you can't take a correlation and imply that there's a cause and effect relationship there. But people do it all the time and make decisions based on it. So if you get a data that you graph it and it looks like maybe a straight line would go through the middle of that and be pretty close, all the points be pretty close to that line, then you're going to say they're correlated. If you look at it and they're just like some random field of dots, then you would say it's not correlated. Right? Nobody would be trying to make sense out of this because it doesn't look like there's anything going on. People would be trying to make sense out of this. It looks like there's something going on. Now, if it looks like the line that you would draw through the middle of those points has a positive slope, and you should know what that means, right? Positive slope means it looks like it's going up from left to right, then that's a positive correlation. If it looks like the line that you would draw through those points would have a negative slope, that's a negative correlation, right? More of one thing leads to less of another. In this one, more of one thing leads to more of another. In particular, we're supposed to understand what a correlation is. We're supposed to understand what a positive and a negative correlation is. I don't see that we're asked to do it. In one of the books I taught out of in the past, they also made a point of what's a strong correlation, what's a weak correlation. So a strong correlation is when all those points are really close to the line. It looks like a line is a good approximation, and basically all the points are really close. It doesn't have to be that close for you to say, I think a line goes through the middle of those points. It could be a little more spread out. That would be a weaker correlation, but it would be there. Okay. So this table shows the lengths in centimeters and swimming speeds in centimeters per second of 6 fish, right? And actually, that's only 5. Man, oh man. We want to graph it and see whether it looks like there's a correlation, right? So let me see. The first one, the length, I didn't even. So let's see, my biggest value here is 37.8. So 1, 2, 3, 4. This is going to be my 40. This will be my 20, 10, 30. And on this axis, it looks like it goes up as high as 148. I think I made this 50, 100, 150. Right, so if I graph these, 37.8, 148. 37 is about right there, 148. 19.2, 47. 21.3, 88. 26.2, 131. That would be about right there. And 26.8, 98. Do you think it looks like there's a correlation there? I mean, can you imagine that a straight line actually might roughly approximate what's going on? In statistics, in the world of statistics, that's a correlation for sure. It's starting to look a little messy compared with the ones we looked at before, but that's clearly, they'd say, yeah, there's a pattern going on there. It's a correlation. It may not be as strong as the ones we've done in the past, but you would say that's a correlation. So graph those points and see whether it looks like there's a correlation. See if something looks like that? Does it look like there's a correlation first? Is it positive or negative? Looks like there's a positive correlation. Looks like you get more of one, you get more of the other. So we should know now that if you can take a scatter plot, you can determine whether the data is correlated. You could draw a line through the middle and come up with the equation of that line, which would give you, some kind of quantifiable relationship between the two. Now, when you draw that line through the scatter plot, that's called a trend line. The goal of drawing your trend line is to minimize the differences between your line and the actual data, which probably means it's going to go in the middle. There'll be some points on one side and some points on the other. Now, you can make that the actual best fit line if you find the actual position that minimizes the error between. And the math you do to figure that out is more sophisticated than we would do in this class. On the other hand, your calculator does it for you easily. It does it for you easily. That's what we've got to learn today. How to use the calculator to find the best fit line through data. There's actually a side benefit to this is, okay, so let's say I give you 10 points. You come up with the best fit line that goes through the middle of those 10 points. But what if I only give you 2 points? What do you think that trend line is going to be? How many lines can you draw through 2 points? Just one. It's going to be that line. If you know how to do what we do today just with 2 points, it'll make the slope-intercept equation of a line for you, which means it'll calculate the slope, find the y-intercept, everything. But we're doing it for more points than just 2 right here. So here's where you got to get the calculator out. And it's also, I should say, a best fit line is also called a linear regression. Linear regression is a term. Regression in general means it comes from the idea that if people are like extreme, let's say your parents are both tall, and then they have you as a kid, it's more likely that you're going to be closer to average than you're going to be tall, right? It's called a regression to the mean. When you take extreme things, usually what follows is not going to be quite as extreme. It's a regress to the mean. So that's where that word comes from. And we'll actually see it in the calculator. You see REG for regression all the time. That's why we just have to mention where it comes from. So with your calculator, so I've given you two sets of data, or X, here's your X's and here's your Y's. So first, we have to enter the data in the calculator, right? To enter it, you go to Stat, it's right there. Edit, which is where it will come up automatically. So you can just hit Enter for that one. And when you do, you should see columns with an L1 at the top of the left column and an L2 right next to it. Do you see that? Got to try it. Stat, Enter, L1, L2. Okay, you're going to put the X values under the L1. So I've already done it for this, but you should do the same thing. Right, 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 8. Every one you enter, you hit Enter after you've done it. So 1, Enter, 2, Enter, 3, Enter, until you get all the way to the bottom. And then you right arrow to go into the L2 column, and it should go all the way to the top. Did you get that? Suf? Why? Enter. Seven plus 7, 1, 2. Stat. Edit. 1. Enter. So you got to get those. Okay, let's go. Everybody got their list of L1 and L2 in there? L1. And it can happen that your columns get off. Somehow you delete the L1 and now it's starting at L2 or something like that. You may have issues if that happens, but we'll see if it comes to that. It's easily fixed. Okay, then we don't actually always have to look at the data if all we're interested in coming up with a line, but actually usually you don't know whether it's a line. So you wouldn't want to go ahead and make a line if it's actually not even correlated. So here's how you do that. You hit the second y equals. So meaning hit this button, second y equals, and you should see this. That screen right there. And you hit 1. You hit 1. Actually, you hit second y equals 1, and you should see this screen right here. Y equals. Okay, everything is right here. Everything you need to see. Okay. So it's probably black on the off, right? But we need actually to turn on the plotting of points. So hit Enter so that it's darkened on the on. Right? This is turning on the plotting of points, which it wouldn't have done otherwise. So are we okay with second y equals? What does it say above y equals? Stat plot. So we're plotting what we just put under stat. Okay. So you hit second stat plot 1, and then it brings up this screen. We hit Enter so that it stays highlighted on. And then to look at the points, hit Zoom, which is right there, 9. Zoom 9. And you should see exactly that. Right? If you don't hit Zoom 9, if, for example, you just hit Graph, right? The graph is going to put it like right in the middle, so the origin is like right in the middle. Sometimes your numbers are like way off the screen. You won't even see them, right? If you hit Zoom 9, it's going to like go so it makes your points right in the middle of the screen. Does everybody see a scatter plot that looks something like that? Micah? Does it look like it's correlated? Does that data look like it's correlated, like a straight line to go through the middle of them? Okay, so since it is, let's go ahead and make the equation of the line. Right? You're going to go stat, the same stat button that we used before. This time you're going to arrow over to where it says calc. right? So stat, arrow over to this one right there. Stat is right there. Okay. Now, look down the list, and number 4, it says LINREG, linear regression. That's going to be the trend line. So that's why we go stat, calc, 4, because we want 4, linear regression. So if you do that, you should see this screen. And notice that it's telling you that the X list for this thing is in the L1 and the Y list is in the L2 because that's where you put them. You could actually put them in different columns and then make it point to different columns, but usually we're going to use L1 and L2. Okay, now you have to hit enter 5 times so this thing moves down the screen and then actually comes up with the equation of a line. So hit enter until you see the cursor going down, and then finally you should come up with this screen right here. What? Arrow over to the calc. No, here, top of the screen. You're not trying very hard. Stat, right arrow, calc, 4. Do it. Stat, right arrow, 4. 4. You don't have to move down. Just hit the number 4. There. Enter. So did you get this here? Okay, so notice it doesn't use mx plus b, it uses ax plus b, but you could tell that the a is the slope because it's in front of the x. So our line, and you wouldn't want to use all of these decimal point places over here. I think I rounded off. I wrote this down. Oops. I wrote it down here. I used 2 decimal places. 1.58x plus 2.30. That's our line that goes through those points. And if you want to see your line go through the points, then go to the y equals, right, top left, and you should see this right here, and put this, 1.5x plus 2.3. And then hit graph, which is here. And see whether you don't see your points with a line going right through the middle of them. Because you didn't do zoom 9. Right? So how are we doing? Did you get it? Did you get it? I would say, because I'm remediating on Algebra 1 right now for kids who still have to pass it that took it last year, there's probably like 5 questions that you have to do this kind of thing on it, on the previous release test. It's a fair amount, right? You want to know how to do this process. Okay, so let's see. So this table shows the total number of CD singles shipped in the millions by manufacturers for several years during the period 1993 to 1997. Again, we're not going to use those years for our X values. How about we say, let's let the X values be the years since 1993, right? So in this case, my X is going to be what? 1993, right? X is years since 1993. So in 1993, what is X? 0, 1995, 2, 1996, 3, and 4. So let's use the calculator to make the scatter plot using these are the X values, the CD sales are the Y values. So that'll be your L1 and L2. right? So remember the steps. Stat, edit. Yeah, well, there's an easy way to do that. I mean, first of all, you could just clear your memory, and that'll get rid of everything. How do you clear memory? Second plus 712, and then go through this process. 4. I don't know why this. I think you can see all the data anyways. I mean, the other thing you can do to clear the data, if you go to stat and you edit, you can go into, you can actually make the cursor go into where it's highlighted on L1 and hit clear, enter. And then I go into the L2, clear, enter. And then I can start fresh. So here we go, 0, 2, 3, 4. And 7.8, 22, 43, and 67. You get it?
Okay, so from here, when you go to the equation, so second one.
Okay. So it looks good.
Okay.
Well, the first step is, you got to get the scatter plot. Yeah. What's that? Get another. So remember, did you get the data in? Second y equals 1. Make sure it's highlighted on. Enter. Now zoom 9. Yeah. Because that's from the last. When you put that other one on there, you need to clear that.
Oh, okay.
Just hit clear. Now go back to the graph. If you still have the line that we drew on the last problem, then just go to y equals and delete the line. So I'm gonna look at the data, right? Second, y equals 1. It's already on, so now I'm gonna hit zoom 9, and there's that. And I still have the line that we did last time, so I'm gonna take that off, clear, and now I'll hit back graph. Okay, now how do I make a line to go through the middle of those points? Nope. Stat, calc, 4, and then hit enter until it goes all the way down the screen. So you should be getting like 14.5x plus 2.4. Are we okay with that? I think, did I put that on the next slide? 14, I'm going to say 14.5 plus 2.4. Did I do? Yeah, I already have it on the next slide. So there's my equation. Let me put it on the y equals 14.5 x plus 2.4. And I hit graph. Does it look okay? Does it look like it's going to the middle? I mean, what we're sure of is that is the least error between a line and those points that you can have. That's what the calculator is doing for us. Okay, now that I've got that equation in the calculator, if, for example, I want to know, remember on our table, we didn't have 1994. What if I wanted to find an estimate for how many CD single sales there were in 1994? What would have been the value of X? 1, right? So go back to the calculator, right, and go to the table of values, right? Second table, and when X equals 1, what does Y equal? 16.8, right? That is the calculator solution for this is it looks like it's 16.8. No, 16.9. Yeah, I can't read it. So you go to the calculator and say 16.9 million. And what about if we wanted to find the sales in 2000? Then what would we look for in the X value? How many years since 1993 is 2000? 7. So use X equals 7 in the calculator. Look down. Now I've got to scroll. 103.9. Okay, when we found for 1994, right, that was like finding a value that was in the middle of the points that we put in there. That's called an interpolation. Interpolation. When we found for 2000, which was beyond our data, that's called extrapolation. Right? We're extrapolating when we're trying to like go beyond our data. Now, the truth is, you got to be careful when you extrapolate, like well beyond the data that you were given, because things might have changed. I mean, this thing in particular, do you think that people buy CD singles now like they did back in 2000? Probably not. You know, this is probably not a good approximation for what's going on today. You know, I think the 1994 that we just had to get in the middle there, that's probably pretty good. At 2000, maybe it's pretty close, but it's probably not good for 2016. So when you've got real data, you're very cautious to go well beyond the data that you were given. So try to make a scatter plot of this. And I'm going to say X equals years since 1995. So you're going to use X values, which are 0, 1, 2, 3, and 4. So stat edit L1, L2 should have looked like this. Make sure that like you don't have like columns that are different lengths. Like in this one in particular, I wrote over the top of my L1s. And then when I right arrowed over, it like went to the bottom of what was already there. And if I didn't delete what was on top of it or right over the top of it, it would have just made the Y column, the L2, longer than the L1. It won't work if you have more data in one column than the other. So you should have exactly like this. And then once the data's in, we can look at it. If you haven't cleared your memory, the stat plot is already on. Just hit zoom 9. Zoom 9. Does it look linear? It looks pretty good, so make the equation. Stat calc 4, enter. (26.6x plus 19.21). No, 1921.4, sorry. I'm losing it. Right, so now I can go back to the calculator and put that. Does it look like a good line going right through the data? Okay, now they want to know predict the floor space in 2010. What will be the X value in 2010? Remember, X is years since 1995. Yeah. 15 years. So go to the table of values, second graph, and see what is the Y value when X is 15. Second. $2,320.4. Again, do you think that this prediction, which was made on the basis of data that was collected in the 90s, would have made a good prediction about 2016? Can you think of anything that might have happened with housing since 2000 or since 1999? How about the whole recession and everything that we just had? That was a housing crisis. So I bet you a lot of people, this looks like housing, the floor space just kept going up and up and up and up and up. I'll bet you it didn't keep going up. At the very least, it leveled off or went down a little bit. People try to save money. Okay. So try to do those two problems. That's it. Two problems. Two problems. How long does it take to do one of these things once you know how to do it? 5 minutes. So you have double that amount of time.